what are called stationary states, what are called
so the probability density.
but we can separate out the space part and the time part. And generally the time part comes as e raised to, let's say, minus iut by h cross. So psi star psi will not have any time dependence. That means probability density is time independent. So if you calculate the expectation value of any operator which doesn't depend explicitly on time, will have no time dependence. That's why they are called stationary states. Okay. So we will start with the stationary state. Suppose in general, if you solve like h psi equal to e psi, the corresponding solution get point later, and also obviously when I use h psi equal to e psi, that means I am talking about time independent framework. Time dependent perturbation, obviously we will learn in detail, say, when we go to the molecular spectroscopy, because there you have to have the quantum dynamics, because the system will evolve when it will interact with the external radiation, so that you can talk about the spectroscopy. So time dependent perturbation, I am keeping it for that particular time. So when we will understand the spectroscopy. So at this moment, I'll just tell you, say, as I consider the stationary states, let's say, of a given problem, suppose if I have many electron atom, how do we write the Hamiltonian? Let's say del I square minus sum over I z by Ri plus say sum over I less than j 1 by Ri j. So this is the kinetic energy operator for all electrons. This is the electron nuclear attraction. This is electron-electron repulsion. Okay. So you can see that in helium atom, 2 electron problem can be written. So another problem, let's say if I call, say, minus h cross square by 2 mu, let's say one-dimensional problem, if I write d2 dx2 plus half. This is the Hamiltonian of which system? You see, a system is identified by its Hamiltonian. This is for which system, this Hamiltonian? What happened? This is one-dimensional and harmonic oscillator. Okay. So you can see that up to this point, this is harmonic oscillator, and these are anharmonicity terms. Similarly, suppose this part basically is independent electrons, because electron-electron repulsion is not considered. So I can solve the corresponding problems if I call this as H naught. Suppose my Hamiltonian doesn't contain this part, or here it doesn't contain this part, and this is the Hamiltonian of that ideal system, like harmonic oscillator or independent particle model. Then I can solve this problem H0, let's say psi k0 as ek0 or ek0 psi k0. So I can solve this problem, but these ek0s are energy eigenvalues for this model Hamiltonian, And these are the corresponding stationary states now, the corresponding wave functions for this particular problem. So what would be my approach now if this quantity is much less than this quantity, or similarly this one is much less in this, which is the case in majority of the situations, then I will consider the spectrum of this problem. Suppose if I call this problem as there, like this one, if I write like psi 0, 0, psi 1, 0, E2, 0, and so on. Energy values for this extra piece on this structure as if this part of the Hamiltonian is going to perturb this setup. So I will call this as a perturbation Hamiltonian, and similarly here I will call this as a perturbation Hamiltonian. And its job is to somehow shape this whole setup. That means it is like this. Say these energy levels will go a little bit down or a little bit up. Similarly like this. So what is the role of this perturbation? The original setup to change little bit. So there will be slight change in the wave function, slight change in the energy values, and that is possible only when you can ensure that your H0 is much larger than HP, or here H0 is much larger than HP, and that is true in many cases. So that you can, in principle, start with the problem with this model, and then apply the perturbation to simulate your real system. Okay, so now we will see how we do it, that we will see, but this is the genesis of the perturbation method. Okay, so here you can see that we are talking about non-degenerate state. Degenerate state is not at all difficult. You have to take the linear combinations, because you know that the, say, linear combination of degenerate states of any, or degenerate eigenfunctions of any Hamiltonian is also eigenfunction of the same Hamiltonian with the same eigenvalue. And that is the reason you can take the linear combinations of, let's say, P1 and P minus 1 and generate Px and Py orbitals. So your starting orbitals, your complex orbitals, even for hydrogen atom, from where you get the real orbitals, which will serve the same purpose, same energy. So you can, in principle, do it. There are certain problems somewhere else, like you cannot talk about any specific ML value, etc. But as long as they are degenerate, you can do this exercise. So degeneracy is not a problem. And here, in this situation, say you have to know how you set the perturbation. Say the perturbation will simply change little bit the corresponding energy level diagram. And here, without, say, sacrificing the whole setup, I can do like successive perturbations, step by step. What is step by step? Here you can see that I didn't bring any external perturbation to my system. The system per se is there, like whether it is, say, helium atom or sodium atom, or an harmonic oscillator, or non-rigid rotator. Okay, the same system is there. What we did, we conceived a model system which can be like analytically solved, and then after getting the analytical solution, so this, if I take the whole Hamiltonian is not analytically solvable. But this part, if I take, this equation is analytically solvable. Similarly, this equation is analytically solvable. Then I see the effect of the external part, which is the perturbation Hamiltonian. So if I call this as the unperturbed Hamiltonian, this is the perturbation Hamiltonian, and this one would be then perturbed Hamiltonian. So this is the Hamiltonian of the perturbed system. Now suppose I apply perturbation theory to find out the wave functions and the energy eigenvalues for this Hamiltonian. Then I say, suppose I inject some external perturbation. External perturbation means, suppose I place it in some external electric field or magnetic field or in a solvent or whatever external stuff, which is not a part of the system. But now I am telling that system is interacting with that external perturbation. Suppose I want to study Stark effect or Zeeman effect or say effect of solvation and so on. Then what I do, you can see that now I am designing two steps. First, go to the system, take the part which is analytically solvable, major chunk of the Hamiltonian, solve it, apply the perturbation which is the remaining part of the Hamiltonian, get the energy eigenvalues and the wave functions, then apply the external perturbation. So now I am bringing in secondary type of perturbation, so that again the further, whether there will be a splitting or there will be some change, etc., that we can understand by applying the external perturbation. That's also perturbation theory. Okay. In fact, what we will see when you go to the spectroscopy, obviously you have to study the matter field interaction, and there that external perturbation is important to understand the spectral transitions. So our starting point is like this. So we keep this at the side. So our goal is we start from here, we generate this. Okay. Now the beauty of this is now I can do some order by order analysis. Say, let's see. So I write first the Hamiltonian as H0 plus HP, which I can write in terms of a perturbation parameter, say lambda H prime, lambda square H double prime, triple prime, and so on. So what I am doing, in this case there is a perturbation parameter. Say you remember when I wrote anharmonic oscillator ax cube plus bx to the power 4, maybe I can write cx to the power 5. So the quadratic part is the linear part, because if you get the force out of it, that would be linear, negative gradient of the potential. And then, so that is linear harmonic oscillator, then all nonlinear terms will come at various orders, that I can write it in this form. Or suppose you are studying something like, say, NMR spectroscopy. Okay, so first term will give you nuclear dipole moment spectroscopy. What is the traditional NMR doing? Then you have nuclear quadruple moment spectroscopy, octuple moment spectroscopy, hexadecapole moment spectroscopy. The hierarchy of such nuclear magnetic resonance you can do. Particularly, suppose if it is blind to dipole NMR. If I equal to 0, you know it is inactive. But still, you can do it. You go for nuclear quadruple moment resonance because often, if dipole moment is not there, quadruple moment is also it is present. So you can do nuclear quadruple moment. So now people are doing hexadecapole moment or also standard spectroscopic technique. So what I'm trying to say, you write it in terms of perturbation parameter. That parameter depends maybe with the make of your system or say the instrument what you have, and accordingly you get the corresponding series. And the corresponding wave functions, say if I write psi k as psi k0 plus lambda psi k prime plus lambda square. And Ek would be so now your job would be, suppose you have H psi k as Ek psi k. So now you can see this is the exact Hamiltonian, and this one was unperturbed Hamiltonian. So suppose if I tell that this is for the harmonic oscillator, this is for the anharmonic oscillator. But as these functions, they are eigenfunctions of a Hermitian operator, I told you that they are mutually orthogonal and they can be normalized. So they will constitute an orthonormal basis set. That means if I call this psi k 0, so your psi k 0 will constitute some orthonormal basis set, and you get psi k 0 psi L 0 is chronic at delta k L. And similarly, from here, psi k psi L is chronic at delta k L. You can see, because these are also the functions, eigenfunctions of the Hermitian operator. And similarly, this is another Hermitian operator. So they are forming some orthonormal basis set. So with this bookkeeping, let's proceed. So what you will have to do, this is the exact equation for the actual problem. Here for H you put this one, for psi k you put this one, for Ek you put this one, for psi k you can put this one, and then arrange it as a polynomial equation in lambda. Okay, I am giving you 5 minutes time. So what you have to do, you put it over here, this, that, and then plug everything, let's say towards the left side, and write it in the form of something lambda to the power 0 plus something into lambda plus something into lambda square plus dot equal to 0. Okay, do it very quickly.
So can you please explain that?
What?
Can you please explain like what we have?
H psi k equal to Ek psi k. For H you put this one. For psi k you put this one. For Ek you put this one. For psi k you put this one. Rearrange them as if it is a polynomial equation in lambda. So you have something into lambda to the power 0, that means constant, plus something into lambda, plus something else into lambda square, plus yet something else into lambda cube, plus dot dot equal to 0. Okay? So simply substitute and rearrange. That's it. Okay? What is the first one? How to get here?
Sir, H0 psi K0 minus epsilon K0 psi K0.
This one.
H0 psi K dash plus H dash psi K0 minus epsilon K0 psi K dash minus epsilon K dash psi K0.
Okay, so you can get term by term. Now you see, because this lambda is arbitrary, in order the sum should be 0 for all, whether you are taking say 1 Tesla or 2 Tesla or 10 to the power 5 Tesla, the equation remains same. So similarly, we are not specifying what is A. So separately, these terms inside the bracket should be 0. So this should be 0, this should be 0, this should be 0. What do I get? If I put this part equal to 0, what do I get?
Unperturbed Hamiltonian.
Yes, unperturbed Schrodinger equation, not Hamiltonian. Okay, so unperturbed equation I am getting as a byproduct because this quantity is not effective. So that's why I get the unperturbed one, isn't it? This one, when I put this to be 0, what I get is called first order non-degenerate stationary state time independent perturbation theory. So this is called first order perturbation theory. If I am not satisfied with this, then I have to go to the second order. And there is a hierarchy depending on what exactly we are doing. Now suppose, say you are studying NMR. The first thing is how the nuclear spin, which is behaving like a magnet, is interacting with external magnetic field. That is the first order effect because that comes as the first order of the external magnetic field strength. Similarly in ESR, but then of course, say one nuclear spin interacting with another nuclear spin, that's the second order effect. One electron spin interacting with another electron spin, that's the second order effect. Or one nuclear spin interacting with one electron spin, that's also second order effect. Do you know what is the name of that? The first order is your Zeeman effect, or say if you are doing something else like start effect. But now what I am doing, I want to go further. So I have several splitting now. You have learned, I don't know, maybe you have some idea of NMR. So then you have to go for spin-spin coupling. And when you have the spin-spin coupling, that's the second order effect. That spin may be two nuclear spin or two electron spin or one electron spin, one nuclear spin, which is known as hyperfine interaction. Okay, so that will give you further splitting to your NMR signals when you go for the high resolution spectrophotometer. But we will consider here only up to the first order. Okay, so if I go for the first order perturbation theory, so if I can solve this equation, basically I am talking about the first order perturbation theory. Okay, remember again, we recapitulate. We could solve the problem unperturbed Schrodinger equation H0 psi k0 as Ek0 psi k0. Now we are seeing the effect of the perturbation H prime so that we can understand what would happen to the corresponding eigenvalue spectrum or the corresponding eigenfunctions of the unperturbed problem. So in this, you can see we know H0, we know Ek0, we know psi k0, we know H prime. Obviously, otherwise we don't know the system we are talking about. But we don't know psi k prime, we don't know Ek prime. These are the two unknowns which we will have to find out now. Okay, so first we will go for the calculation of the energy. As you have seen that first we solve for the eigenvalue and then we go for the eigenfunction. So we rearrange this equation. Say once again, let's recapitulate. We know this one, H prime we know, psi k0 we know, Ek0 we know. We don't know Ek prime, we don't know psi k prime. So psi k prime is an arbitrary function, okay, unknown function. But we know in linear algebra that if you have a set of, let's say, simultaneous, say, if you have a set of orthonormal basis functions like psi k0, I can write any function as a linear combination of those functions, sum over L, L, psi L, 0. So we know that any arbitrary function can be written as a linear combination of the corresponding basis functions. And these basis functions are orthonormal because they are eigenfunctions of a Hermitian operator. Okay. Now you can see this is an operator. H0, Ek0 is an operator which is operating on the sum. And there is some constant sitting over here. Now, what I will have to do, I will take this operator to this place. Look, I'm entitled to do this. Why? Can you tell why I am entitled to do this? Look, this is constant, this is a linear operator. Remember, I told you in quantum mechanics, all operators are linear Hermitian operators. Linear operators means it is closed under addition and scalar multiplication. That means this operator operating on a sum is same as sum operating on the base. Okay. Similarly, this is the scalar multiplication. So it is linear operator, I can take it over here. And if I take it over here, what it means h0 minus ek0 psi l0 operating on ek0 operating on psi l0. But h0 operating on psi l0 is what? h0 operating on psi l0 is what? From unperturbed equation. H0 operating on psi L0 is what? You know, H0 psi K0 is K0 psi K0. K is a dummy. So if I say L for K, what shall I get?
EL0 psi L0.
Okay, that means H0 psi L0 is EL0 psi L0. So this will give me EL0 psi L0, that means EL0 minus EK0 psi L0 with AL over K. Okay, so let me rewrite again. Is it okay? Are you getting it? Okay, now this is just a standard technique. I will left multiply by psi k0 star, both sides, left multiply by psi k0 star, and then integrate. So I'll do this operation. First I'll left multiply here because operators are there, so I should be careful. Left, right, the order is important. So psi k0 star, I will do the left multiplication, and then I will integrate. If I do this, suppose if I do psi k0 star, again summation is there, so I can put psi k0 star on all the terms and then integrate. So I get here sum over L, AL, EL0 minus EK0, and this one would be psi k0 star, psi L0. This integral, but this integral we know this is chronicle delta K. And this one would be minus psi k0 star H prime psi k0 plus EK prime psi k0 psi k0. Okay, so this term we know this is the matrix element. We have already learned the matrix element of the operator. So this is the matrix element. This is minus H prime KK. Okay, this is the KK matrix element of the H prime operator. And this one is 1, isn't it? Because this is the orthonormal set. So psi 0 star psi 0 integral is. Can you tell what is the left hand side? What is the left hand side? What would be there in the left hand side? Can you tell?
0.
Yes, it should be 0. You see, this would be 0 for all terms, for all values of L except when L equal to K. But when L equal to K, this term is 0, isn't it? For L equal to K, this is 0, and for all other L other than K, this is 0. So this whole summation is 0. So what it says that your Ek prime is just H prime KK. If I rearrange this, I get my Ek prime as H prime KK. That means the first order perturbation correction to the energy is the expectation value of the perturbed Hamiltonian, perturbation Hamiltonian over the unperturbed states. Okay, so you don't need the perturbed wave function to calculate the first order correction, perturbation correction to the energy. That means in this case, the energy would be energy up to first order is Ek0 plus lambda H prime Ek. So you can see that if I apply first order perturbation theory, I can calculate the energy in terms of the unperturbed problem. I have to calculate this, and again, calculation of this, you can use the numerical quadrature, which you have learned already, isn't it? So you write the perturbation Hamiltonian, get the corresponding unperturbed wave functions, calculate the integrals using trapezoidal rule, Simpson rule, or whatever, and then you add to the corresponding energy, and you can do it for all the states. You can see this K maybe 0, 1, 2, that means ground state, first excited state, and so on. So your perturbation theory, let's say at the first order, if you want to calculate, that will give you, say you are getting the energy eigenvalues of an harmonic oscillator in terms of harmonic oscillator energy values, or let's say some independent particle problem will give you some interacting system like helium, neon, etc. So I am giving you two problems. Say wave function, I will tell you just the next one is to get the first order correction or the first order corrected wave function. But before that, let me just tell you about this problem. To solve or get the energy eigenvalues of the helium atom and an harmonic oscillator up to, let's say, quartic term using this formula. These are available everywhere in any standard textbook or if the website you go. How to apply first order perturbation theory to get the energy for helium atom and also for an harmonic oscillator. So these are the two problems I am giving you just to try to solve them. Now we will go for the wave function. You can see that we could get the energy using first order. Now for the wave function, we start again from the same equation here. Say I pre-multiply now by psi j 0 star where j is not equal to k. Previously we did it with k, but now deliberately we are doing any j principle. Can you tell what will you get? You do the same algebra as you did before. What do you get? So we have solved half of the problem. So you know the energy of the system. And here you can see, again I am telling you, if I have some external perturbations, so after I get the energy and the wave function of, let's say, helium atom, now I can place the helium atom in some external electric field. I apply the same, but now my EK0 would be the energy eigenvalues of the helium atom, not of that independent particle. Okay. So if I multiply, pre-multiply by this and integrate, what do I get? Okay, so this becomes sum over L, AL, EL0 minus EK0. This one would be psi J0, psi L0. This is minus H prime JK, plus this is EK prime, psi J0 star, psi K0. Okay. But this one is Kronecker delta Jk, and we have chosen J which is not equal to K. So this term becomes 0. Okay. What about this? Here you can see that this one is Kronecker delta JL. So this will be non-zero only when L equal to J. For all other L, this will be 0. That means from here, what I get sum over, sorry, no sum. AJ, EJ0 minus EK0, this is 1 minus H prime JK. Okay. This one has become 0. Or AJ is minus H prime JK by EJ0 minus EK0 for all J not equal to K. Okay, so for all J I can write this. Now look.
Excuse me, sir.
What?
Sir, can you please explain this again?
Psi J0 star, I am left multiplying and integrating. This just as before. Is it okay? Previously I did it with psi K0 star, now I am doing psi J0 star with J not equal to K. Okay?
Yes, sir.
So this is Kronecker delta J. This gives me this matrix element, and this one gives me 0. So now what I have done, from this summation, only one term will survive when L equal to J. So L equal to J means this becomes AJ, this becomes J0 minus EK0, and this is 1. And that is minus H prime JK. So AJ is, I am taking EJ 0 minus EK0, so I get AJ. Okay? Any
Yes,
problem?
yes, sir. Now it's
Now here you can see I know AJ everything over because this is my unperturbed problem and this one is the perturbation Hamiltonian that we know and the matrix element is calculated over the unperturbed wave function. So these all A's are known except AK. I don't know AK. So I have to do some jugglery now. And that's important that I will do. Okay, so you remember what is AJ? You remember this one. So AJ, everything, all AJs are known except AK. Okay, now equation theory. What is psi k? Psi k according to first order perturbation theory is psi k 0 plus lambda psi k prime. Look, so this is the wave function of the system if we apply first order perturbation theory. Is this okay? Like the energy, this is the wave function. Now this psi k prime, how we are treating? This is psi k 0 plus lambda sum over let's say L AL psi L 0. This is something what we are treating. So I can write it like this: AK psi k 0 plus lambda sum over J not equal to K AJ psi k 0 plus lambda AK psi k 0. This summation is for all L. So I have separated out all values of L except K. So what I have to do, I have to add specifically this case because we know all edges, psi zeros are of course known. Lambda is coming from your problem. I don't know AK, isn't it? So I have to do something to get there. Rest of the terms, everything we know except this AK. Okay. Now, see what is psi k star then? This is psi k 0 star plus lambda sum over J not equal to K AJ psi k 0 star plus lambda AK psi k 0 star. Okay. Just I am taking the complex conjugate of this function now. Now can you calculate this? Now this quantity psi k, you know that this is 1, isn't it? Because they form the orthonormal set, so this is normalized. Psi k is 1. But what is psi k? So you have this over here and this, and then you integrate. So what do you get? Again, I can write it in some lambda. So tell me what will you get? This is your psi k, this is your psi k star, and this is psi k star, psi k d tau integral. So how do you get this? Okay, so first this into this and then integral. So this cycle 0 start. Then if I go for this and this, I get lambda sum over aj cycle 0 star psi j 0, and this into this again I get the same thing. So plus 2 times lambda yes sum aj this is Kronecker delta jk. Then I get this and also I get this. Okay. So plus I will take this place. Plus lambda square to 0. Now what is this? Because it is j not equal to k, we know that Kronecker delta jk would be 0 when j not equal to k. It would be 1 only if it is j equal to k, but that is not there. That means this term becomes 0. What about this term? What about this one? This should be 1. It's normalized, isn't it? If you don't follow, tell me. Is it okay?
Yes, sir.
So now here, this one is 1. So if you have 1 on the left hand side and here it is 1 plus something, that means this term is 1 and the left side is 1. So 1 plus whole stuff equal to 0. That means this whole stuff must be 0. Isn't it? Tell me whether you follow the logic. This 1 equal to 1 plus something, so that was that something must be 0. Come on, tell. Any problem?
No, sir. Yes, it's fine.
Now, so this term is anyway 0. Now, if it is lambda, again we apply the previous logic. So whatever is the coefficient of lambda separately, that should be 0. Whatever is coefficient of lambda square, that should be 0. So I don't bother about this part. This is 0. This part is 0. But here you can see this is 2. This lambda is non-zero. Otherwise, you go back to the unperturbed problem. This one is 1. That means what it says, ak equal to 0. We have done such lengthy exercise just to prove that ak equal to 0. Do all of you follow why we get ak equal to 0? Simply what we did, 1 equal to 1 plus something, and we have shown that something to be 0, because 1 equal to 1 plus whatever, that must be 0. And then we analyze various terms as 0, so only one term we are interested in now. That part is 0, and that tells us that AK must be 0. If AK is 0, now you can see this was my psi k prime. So what we get, AK equal to 0. So I don't have to bother about this anymore. This is what I have. Is it psi k or psi k prime or psi k? This one? Psi k 0 plus lambda sum over j not equal to k, Aj psi k 0. This term becomes 0 because AK we have shown to be 0. I will not proceed if you don't say that you have understood. Up to this point, is it okay? You check the steps and tell me. Okay, let me write the final result and then I will ask you. So this means, so EK, we got EK 0 plus lambda H prime KK, psi k is psi k 0 minus lambda sum over j not equal to k, Aj size is 0. So Aj means H prime jk by Ej0 minus Ek0 size is 0. Just I put the Aj values here with the minus sign, size is 0. Here you see that everything is known. These are your unperturbed problem. This is the perturbation Hamiltonian matrix element over unperturbed states. This is the perturbation parameter coming from your problem. So we could calculate the energy and the wave function. That means we have solved the corresponding Schrodinger equation of the perturbed problem, because once we solve the Schrodinger equation, our main aim is to get the energy eigenvalues and the wave functions. So we could get the energy eigenvalues and the wave function up to the first order perturbation theory. Do all of you follow till the end? If you are interested, you can get the wave function of the hydrogen helium atom also, but I'm not prescribing. But it is also you can see there nothing difficult. Okay, so you start from here, or you try to get the wave function of some anharmonic oscillator, starting from harmonic oscillator wave functions. You can do same thing for getting non-rigid rotator in terms of rigid rotator wave functions. Now just tell me whether there is any step which you could not follow. So here what you could see, your main job, whether to get the energy or the eigenvalue, this calculation of the matrix elements. And calculation of the matrix elements, many times you may not do it, be able to do it analytically. So you can apply numerical techniques and calculate those. And that will solve your problem. So now tell me whether there is any problem in getting these expressions. Okay, so at least the helium atom problem you must solve. Okay. Maybe that would be your third assignment. I will tell you later. Helium atom problem, first order perturbation calculation to get the energies. If you wanted to do anything, these are there in standard textbooks. Come on, tell me. Do all of you follow? Do you have any trouble in getting into these two expressions?
It is clear, sir.
What?
It is clear, sir.
It is clear. So, okay, fine. So you know what you're supposed to do. First of all, I reiterate your second assignment. That would be Hunt's equation. And this one you do, this is a part. So I will tell the third assignment later, because there is another component I will just add, so that will constitute the full course of the third assignment. Okay, so if you have no trouble, so let's call it a day. Okay.